Hello everyone, welcome to my continuation video on related rates. So this is the second video and we're going to continue with some practice problems. So the first example we have here is the length of a rectangle is decreasing at a rate of 2 meters per second. At the same time, the area is increasing at a rate of 40 meters squared per second. At what rate is the width changing when the area is 200 meters squared and the length is 20 meters? So always begin by sketching the situation. We're dealing with a rectangle. Okay. I'm going to call the width x. We'll call this the width. Actually, let's call this the length. Doesn't matter how you label it. We'll call this y, and this is the width. I think it's customary to do it this way. And capital E is the area. So the length of a rectangle is decreasing at a rate of 2 meters per second. Okay, so we're talking about the length and it's decreasing. So there is a change. Looking at the units, it's meters per second. So that's a giveaway that we're working with the derivative here. So the derivative of the rectangle, of the length of the rectangle, so that's x, is changing, but more specifically decreasing at a rate of 2 meters per second. So dx dt, the change in x with respect to time, is going to be not 2 meters, but negative 2 meters per second. Because, again, it's decreasing, it's getting smaller. So the length here is getting smaller. At the same time, the area is increasing at a rate of 40 meters squared. So we have the word increasing keyword, and we're talking about the area. So it's not the actual fixed distance of the area, not fixed distance, the fixed area. It's the derivative of the area. So we're talking about the change in the area with respect to time. We're talking about dA dt. So the area is increasing, so we know it's going to be positive at a rate of 40 meters squared per second. So this is 40 meters squared per second. Okay. At what rate is the width changing? So the question's asking us about the width and the fact that it's changing. So what it's really asking us is not for y, which is my width, it's asking us to find the dy dt. That's what the question's asking us for. Okay. So that's our unknown variable. That's the term or the variable we're looking to solve. When the area, the actual area here, now it's a fixed amount. Notice the units are just meters squared. It's not meters squared per second. So that gives away that the area is 200 meters squared. And we get the length is 20 meters. So the actual value of x, which is our length, is 20 meters. Okay, so we're dealing with rectangles and areas. So right away, go write down your formula. The formula for the area of a rectangle is area equals length times width. But instead of using L and W, be careful you don't want to introduce extra parameters. My length is x, my width is y. I'm going to use A equals x times y. Second part of related rate problems, we take the derivative with respect to time on both sides of the equation. So we're going to take the derivative of the area with respect to time and the derivative of x times y with respect to time. Okay. So derivative of A, that's fine. We'll just leave it as is. So the derivative of A is essentially 1 times A prime, which is dA dt. That doesn't change. Here, what you have to catch, and this is a common trick, is the fact that we have a multiplication. We're taking the derivative of two functions that are multiplying. What do we have to use? Product rule. So f times g prime, it's the derivative of the first times the second plus the derivative of the second times the first. So don't forget to apply product rule. So we're taking the derivative of x first with respect to time. So the derivative of x is dx dt, because the derivative of x is 1, and then we get our x prime due to chain rule. Then we multiply by y, we don't touch it, plus, now we're going to take the derivative of y. So the derivative of y with respect to t is 1 times dy dt, and then we leave the x times x. So what we're looking for is dy dt. This is the term that we're looking for. That means we need to know everything else in order to solve for this parameter. So dA dt we have, that's fine. dx dt we have, -2. Y we don't have, we're missing the y. We're gonna have to think of how to find that. dy dt is what we're looking for, and x we have, it's 20. So the only piece that we're missing of the puzzle is y. So to get the y, what you have to do is you have to take the actual formula that we're using, area equals x times y, and solve for the missing value. Okay, so we know the area of a rectangle is x times y. We know the area is 200. We're just going to directly substitute. And then x we know is 20 times y is what we're looking for. So to solve for y, we just divide both sides by 20. So 20 divided by 20 leaves us with y, and 200 divided by 20 is just 10. So our value of y is 10 meters. Now that we solved that, we're going to substitute everything into our equation. So dA dt we know is 40 meters squared per second. Dx dt is -2. Y we know is 10, plus dy dt is what we're looking for, and x we know is 20. And it's always a good idea before you solve just to look at the answer that you anticipate the answer that you're going to get. So we're talking about the change in y. If the length is getting smaller and the area is getting bigger, would you expect the width to be getting bigger or smaller? Do you expect your answer to be negative or positive? Well, if the length is getting smaller and the area is getting bigger, the only thing that's possible is for the width to get bigger. So we do expect the derivative of the width to be a positive value. So keep that in mind, that's always good to know. So here we get 40 equals -2 times 10 is -20, plus dy dt over 20 times 20. Bring the 20 over, we get 60 equals dy dt times 20. And now we're going to divide both sides by 20. I don't have room, so 60 divided by 20 is just 3. This implies that, let me write it here, dy dt equals 3 meters per second. So the width is positive, it's getting bigger at a rate of 3 meters per second. So I would classify this next example as one that's slightly easy. So I encourage you to pause the video, try to solve it on your own, and then compare your answer with mine. So the radius of a spherical balloon increases at a rate of 5 centimeters per minute. How fast is the surface area of the balloon changing when the diameter is 40 centimeters? Okay, so we're dealing with a spherical balloon. This is our solution. It's a sphere. Okay. The radius of the spherical balloon increases at a rate of 5 centimeters per minute. So we're dealing with the radius. That's your r. Since we're talking about a rate, this is our dr dt. It's the rate of change. So that's 5 centimeters per minute. And because it's increasing, we know our derivative is positive. Okay. If it was decreasing, or if the balloon was getting smaller, we would be putting a negative here. So be careful for that. How fast is the surface area of the balloon changing when the diameter is 40? So it's talking about the surface area of a balloon. So the surface area or total area of a sphere is 4 pi r squared. And now that we have our formula, the next step is to just take the derivative with respect to t. So we're going to derive SA with respect to t, and we're going to derive 4 pi r squared with respect to t. Next, derivative of surface area is just the derivative of the surface area, nothing to do there. That's what the question's asking us for. How fast is the surface area of the balloon changing? So that's asking us for the derivative of the surface area. And since the radius is increasing, we would expect or anticipate our answer to be positive, because if the radius is increasing, the balloon's getting bigger, which means the surface area in turn is getting bigger. So they tell us also that the diameter is 40 centimeters. So D is 40 centimeters. So I'm at the stage where I'm deriving both sides with respect to t. So notice that over here it looks like product rule because you have 4 times pi times r squared. It's not, because 4 pi is a constant multiple, so we could just leave it. All you're really doing is taking the derivative of r squared with respect to time. So you could apply a product rule, it's longer, you don't have to do it that way. Here it's just power rule. So we take the derivative of r squared, which is 2r. But then because we're deriving with respect to time, with respect to t, a different variable, we have to apply chain rule, so times dr dt. So in order to find the surface area, or to change in the surface area, well, that's what the question's asking us for, we need the radius of the sphere, and we need the change in the radius with respect to t. of the sphere. So the change of the radius with respect to time is 5 centimeters. So we have this. All we're missing is the radius. But they gave us the diameter. So if we have the diameter of the sphere, let's say top to bottom, that's the diameter. And that's 40. Dividing it by 2 is the radius. So this means r is 20. So simply substitute your parameters, your variables in, and solve for the change in the surface area. dSA over dt, 4 pi 2, radius is 20. Change in radius with respect to time is 5. So 2 times 20, 40 times 5. Let's do this. 20 pi times 40, 800 pi. This is the change in the surface area. So surface area is centimeters squared, and we're per minute. It's positive as we would expect, and that's the final answer. So in this next example, we have an ice cube which is melting at a rate of 2 millimeters cubed per second. How fast is the surface area changing when the cube is 5 millimeters tall? Let's go ahead and solve this. So let's draw our ice cube. It's a cube. So we have a square, square, connect them. So this is our ice cube. And it's melting at a rate of 2 millimeters cubed per second. So the units give it away. The 2 millimeters cubed is, first of all, it's cubed, it's talking about the volume, and it's per second, so there's a rate of change. So we know that the volume is changing. So we're looking at dV dt is 2 millimeters cubed per second. And because the volume is decreasing, it's melting, we have to put a negative sign in front. Okay. So this piece is done. How fast is the surface area changing? So it's talking about the surface area of a sphere, not the sphere, sorry, of a cube. So the surface area, how fast is it changing? So we're looking for a change in the surface area. So we're talking about the derivative of the surface area. How fast is the surface area changing? So if the volume is decreasing, the ice cube is melting. Would you expect the surface area to get larger or smaller? Okay, so you should anticipate whether your answer should be positive or negative. Clearly your answer here should be negative. And then it's telling us when the cube is 5 millimeters tall. Okay. So we have, we're asked to find the derivative of the surface area. So what I would do is start off with writing down the formula for the surface area of a cube. So the surface area of a cube, or the total surface area, is 6 sides squared. Let's call this s, little s, for the side length. So it's going to be 6s squared. Taking the derivative on both sides, because remember, do not substitute the 5 in too early. If you do that at this stage and then take the derivative, you're going to lose the right hand side of the equation. So don't substitute until you take the derivative. So here we're taking the derivative with respect to time on both sides of the equations. So d dt of 6s squared. So the derivative of the surface area is just the derivative of the surface area. And the derivative of 6s squared with respect to time is 6. That's a constant multiple. It sits on the outside. And the derivative of s squared is 2s. And because we're deriving with respect to time a different parameter, it's ds dt. Okay. So the derivative of the surface area is what we're looking for. To answer the question, we need s, which we have. S we know is 5, so we could plug that in. And ds dt is what we need. We do not have any information on the change of the side length of the cube. We know that the volume is changing, but we don't know anything about the side length of the cube. So at this stage here, we're stuck. So when this happens, you have to use another formula. We have to go get ds dt. How? Well, we happen to use the change in the volume. So what do? Take the volume formula and take its derivative. So we know the volume of a cube is side cubed. Let's go ahead and take the derivative on both sides. So d with respect to t, obviously, because it's related rates, we always take the derivative with respect to t for related rates, as cubed. And the derivative of v just stays the same. The derivative of v is 1 times dv dt. And the derivative of s cubed is 3s squared times the derivative of s with respect to time. Okay. So we have dv dt, this information is given to us, it's -2. We have the side length, it's 5, this is given to us. We could find our ds dt. Then once we get our ds dt, we could substitute that answer into this equation, allowing us to find the change in the surface area of the cube. Okay. So this is a tough problem where you require two formulas to derive, but this is the concept. So replace dv dt with -2. -2 equals 3. S squared is 5 squared, so 25, times ds dt. 3 times 25 is 75, and if we divide, we get -2 on 75. So I don't have space to write it, so ds dt, you can do it on your own, you get 75, -2 on 75. This is change in the side length with respect to time, giving us -2 over 75 millimeters per second. Okay, those are the units. And now we just substitute this into our other equation here, giving us that the derivative in the surface area with respect to time, the change in surface area, is equal to 6 times 2. S is 5 times 5, and ds dt we just found was -2 over 75. Okay, let me use a calculator. This gives us 6 times 2 times 5 divided by 75. I'm getting about -1.6. Change in surface area. Surface area is millimeters squared per not per second, per minute. Oh no, it's per second. And that's the final answer. And the fact that it's negative makes sense because, again, the volume is decreasing. We'd expect the surface area of the cube to decrease as well. So in this example here, we have a cylindrical tank with a height of 12 meters and a volume of 1,200 pi meters cubed is being filled with water at a rate of 2 pi meters cubed per hour. How fast is the height of the water changing? Let's go ahead and do that. So we're starting off with a cylindrical tank. So let's go ahead and draw our cylinder. This is our tank. It has a height of 12 meters. 12 meters. We could call this, we could call it H. And a volume of 1,200 pi. So we know the volume is 1,200 pi meters cubed, being filled with water at a rate of 2 pi. Let me just write the radius. We'll call that R. It's being filled with with water at a rate of 2 pi meters cubed per hour. So what does, we dealt with the 12, we dealt with this, and we have to figure out what the 2 pi represents. Since the 2 pi is increasing at a rate of 2 pi, look at the units, meters cubed per hour. The fact that it's meters cubed, it's talking about volume, and since there's a rate, we know it's a derivative. So filled with water at a rate of 2 pi meters cubed per hour, this is the change in the volume with respect to time. It's the derivative of the volume, giving us 2 pi. And since it's being filled with water, we know it's going to be positive. The height of the water should increase. So how fast is the height of the water changing? We're not talking about the height, we're talking about the height of the water. So dH dt, the change in the height. Okay, and we do expect our answer to be positive again because the rate of the volume increase is increasing. Therefore, the height of the water in the tank should increase and be positive. So we're dealing with water in a tank. So we're dealing with volume. So let's go ahead and write down our volume formula. So the volume of a cylinder is area of the base times height. The base is a circle, so area of the base is pi r squared times the height, h. Next, what we do is right away we take the derivative. Again, don't substitute the variables at this stage. Take the derivative first. So the derivative of v divided by dt is equal to the derivative of pi r squared times h with respect to t. Okay. So pi is a constant, so we could just pull it out. We have dv over dt equals pi And if I take out the pi, we're left with r squared times h. What you have to catch here, and this is super important, is the fact that r squared times h is a product. We're multiplying two terms. So we have to use product rule. So recall, for product rule, f times g prime, the derivative of the first times the second plus the derivative of the second times the first. Not squared, derivative. So the derivative of r squared is 2r, but since we're deriving with respect to t, it's times dr dt. Essentially because the parameters are different. Times h, because we're going to leave it, so derivative of the first times the second, so the h stays, plus the derivative of the second, which is h, so the derivative of h is 1, but since h and t are different, it's dh dt, times r squared. This is our derivative. So now we have to go ahead and solve for the height, the rate at which the height is changing. So we're looking for this piece here. In order to find this piece here, we need to have all the other variables. Okay. So the change in the volume with respect to time is 2 pi. This piece we have. Pi is a constant, that's okay. 2 times r. Do we have the radius? The radius was never given. So we don't have the radius. Do we have dr dt? Dr dt wasn't given. Do we have the height? Yeah, the height we have is 12. Then we have plus dh dt, which is what we're looking for. And then we're left with r squared. So r squared is the radius squared, which again, we don't have. So how are we going to find the radius? Well, the information that we haven't used yet was the fact that the volume is 12,200 pi. Let's go ahead and use that. So using the volume formula, V equals pi r squared times h, we could work backwards and find the radius. So this is not an issue. We know the volume is 1,200 pi, so let's go ahead and substitute that. And we know that the height is 12. So we could go ahead and solve for the radius. So we could divide both sides by pi. Let me just move the derivative of dv dt. I'm going to plug it in right away. This is 2 pi. This. We divide both sides by pi, leaving us with 1200 equals r squared times 12. We could divide by 12, leaving us with 100 equals r squared. And then the last step, you square root both sides. The square root of r squared is r, and the square root of 100 is 10. Plus minus 10, but again, the radius can't be negative, so we take r to be positive 10. Okay, so we got the radius, that's great. So let's go ahead and plug it in. Pi 2 times 10, but we don't have dr dt. So this is why it's important to sketch the drawing. This is going to help you understand these types of problems. Dr dt wasn't given. What is dr dt? It's the change of the radius throughout the problem. So as this cylindrical container is being filled with water, we're pouring water into it, it's being filled, how is the radius changing throughout that process? Well, the radius does not get bigger or smaller, it stays the same. So the change in the radius is 0, right? Because as you're filling this up with water, it's not getting wider or getting smaller, it's staying the same. So the change in the radius is 0, dr dt is 0. So they didn't give us that information, but based off our drawing, we have to understand the situation. So this is times 0, and then times height, which is 12, plus dh dt times the radius squared, which we found was 10 squared, which is 100. So dividing by pi, these guys cancel. We're left with 2 equals 2 times 10 times 0 times 12. That's all 0, that's gone, leaving us with dh dt times 100. I don't have space, but we're essentially just dividing by 100. 2 divided by 100, we get the change in the height with respect to time is 1/50. The units are meters, and the time is in hours. So 1/50 meters per hour. That's the change in the height. The fact that it's positive makes sense because again, we're filling it with water, and we're done.